All right. So before we get started, we want to get to know you guys a little bit. So could you please raise your hand if you are using Kafka in production right now? Okay, could you keep your hand raised if you process 1 million messages a day? How about 1 billion? Anyone process 1 trillion? No. Okay, well, welcome to our presentation, everyone. My name is Kevin, and I'm here with Na and MAULIN, and we are from right here at PayPal. So today we will be talking about Kafka at PayPal and our journey to enabling 400 billion messages a day. So let's get started. This is the agenda for the session. We will start with some details about PayPal and Kafka at PayPal in its present state. Then we'll jump straight into the journey with how we began using Kafka, how we experienced a massive growth spurt which led to various challenges, and our road to overcoming these challenges through Kafka as a service. Finally, we'll end with some notes about what the future has in store for us. So PayPal, in case you don't know, we are a global payments processing company, and we have been experiencing tremendous growth over the past few years. I won't go into specific numbers here, but you can see total payment volume has increased dramatically year over year. And you might be wondering, what does any of this have to do with Kafka? Well, it's all about the data, of course. As we are seeing an increase in total payment volume, we are seeing an even bigger increase in the amount of data that we have to process. And we leverage Kafka heavily here. So it's very important that our Kafka infrastructure can scale and handle this growth to keep business operations going. As mentioned in the title slide, our Kafka ecosystem processes 400 billion messages a day. We have over 50 clusters, over 3,000 topics, and totaling 7 petabytes of disk space. We've also been using Kafka for quite a while now, starting with version 0.8, and today our current version is 1.1. Our tech stack has also grown enormously over the past few years, with clients using languages ranging from Java to Python to Node.js. And we have many different types of application frameworks connected to Kafka. Gimmo and Scubes are two actually open sourced by PayPal. Gimmo is a big data framework that provides a unified data API for accessing data from storage such as HDFS and Kafka. And Scubes is a highly scalable asynchronous platform for data processing applications like Kafka. Our clusters are also multi-tenant, which means each cluster is generic in the sense that we have multiple use cases in a single cluster. And our ecosystem is distributed across multiple regions and different availability zones. So let's take a minute and look at some pipelines. On the left side, you will see some Kafka use cases at PayPal. We've got user behavioral tracking, experimental like A/B testing data, merchant SLA monitoring, and risk and compliance analytics. So all these use cases will generate data in the form of a business event, an application log, an application metric, or any combination of the three. And all this data will pass through Kafka using batch processing or real-time streaming and end up on the right-hand side in frameworks and platforms land, where they will be consumed and used for analytics or other kinds of processing. Now you can see that we've got the double arrows going because we have many use cases that involve multiple hops. So for example, data will go into Kafka, it will get consumed by a framework, additional data will get pumped back into Kafka and consumed by yet another framework. We also have some use cases that leverage multiple different types of messaging products, and it's very common for different teams to own different parts of an end-to-end pipeline, so we've seen some pretty complex flows here. Now, let's take a step back and rewind a few years to the beginning. When Kafka first started getting popular at PayPal, individual teams very quickly wanted to use Kafka, and they did by setting up their own clusters. Now, this posed many challenges as they were duplicating work. There was a lack of standardization, they were inexperienced with the Kafka codebase, and there was no knowledge sharing. So all this made it very difficult for them to manage and maintain these clusters, especially as their usage grew. When Kafka became big enough at PayPal, it was decided that a dedicated team would be formed to manage everything Kafka related at PayPal. So this allowed the application teams to focus on building their applications as opposed to managing a bunch of clusters. Soon after the Kafka team was formed, we experienced a massive growth spurt as Kafka became more popular in the industry. From 2015 to early 2017, Kafka traffic grew dramatically as we created many new clusters and expanded existing ones. We saw our Kafka ecosystem expand to a massive scale as we onboarded massive new use cases involving ETL, logging, and high throughput metrics. We very quickly went from processing 100 million messages a day to 1 billion to 100 billion messages a day. And this was a very exciting time to see so much growth happen. But as we rapidly expanded, we began to run into various challenges. The first challenge was that everything was manual and bare metal. We didn't have automated tools to do simple things such as set up a new broker or set up a new mirror maker, so operational work always took a long time. It would take up to months just to onboard a new use case, especially if a new cluster was required. The second challenge was that there was no visibility into cluster health. Sometimes a broker would be down, and we would not know until a client told us. The TTD, time to detect a broker failure, would last up to 24 hours at sometimes. The third challenge was when issues happened, it took a long time for our engineers to debug and resolve these issues. The TTR, time to recover, would range from days to up to a week. Now, this was especially a nightmare when our engineers were paged and woken up in the middle of the night to debug cluster issues. And many times, the solution was just to simply restart the brokers to apply a quick fix. And finally, our software engineers, our software developers, found themselves spending more time doing support and operational work as opposed to writing code, which is what their job title suggests. So to overcome all of these challenges, we created a plan to tackle them in iterations. Our first goal was to provide an operational dashboard and to improve client visibility. This led to our first important project started in 2015, Kafka MAULIN. So Kafka MAULIN is our monitoring and operational dashboard that enables both clients and operators to view and manage their Kafka components. A few notable features are the ability to view the status of any Kafka components, to create, modify, repartition topics, to deploy and manage brokers, zookeepers, and mirror makers, and to view the logs of any of these above components. All of these features are available through a user interface, so people don't have to SSH into hosts or run custom shell scripts just to do things. After developing Kafka MAULIN, we decided to shift the focus to the client side. The challenge we were facing was our clients would come to us and ask us about how well their applications were performing and if they were even performing at all. They would ask us questions like, what is my availability and what is my latency? And we were unable to provide them an answer because there was simply no good way of measuring these things from just the server side. Additionally, we couldn't really detect issues beforehand, before the clients reported them to us, because many client issues are isolated to the client side. So when we looked at cluster-wide health metrics, there would be no indication of an issue happening. This led to a drift between the availability and visibility of the clients and the servers. So we had to fill this gap. And to fill this gap, our solution was twofold. First, we created a canary application that sends and receives heartbeat messages to all of our Kafka clusters. This canary application serves as sort of a baseline or a sanity test application in which if we notice something wrong with the canary application, then there's something likely wrong with the cluster that it's talking to. The second part of the solution is we created a monitoring interceptors library that gets attached to all of the clients to retrieve and publish client-side metrics. We also created a custom send availability metric that gets published alongside other JMX metrics like latency and throughput. And all of these metrics get published to a time series database where we have alerts configured to notify us when things go wrong, such as availability dropping down. Additionally, all of these client-side metrics are available through various pages on our Kafka MAULIN dashboard. And today we have over 4,000 clients monitored by our monitoring interceptors library. So this is a quick screenshot of the canary page. You can see the top portion shows a few graphs, and the bottom portion will list out all of the clients that are part of this application and a few interesting metrics like availability and latencies. And all this data is being fetched from our time series database. So with these two things, the canary application and the monitoring interceptors library, we were finally able to get a look into the client side and to be able to monitor the clients. But our customers kept asking us about the most fundamental question in any messaging.
Consumers. All those auditor messages are consumed by our streaming auditor application. This data loss auditor application will catches and aggregates all the message count from both the producer side and the consumer side, and then compare the total number of messages on both sides to decide whether these are data loss or not. Then the auditor application will calculate data loss for each consumer group. If data loss is detected, the auditor application will send our alert to pager duty. Pager duty is an alert system is used in PayPal. So when alert happen, it will send text message to the support engineers. In the meanwhile, the auditor application will send all the message count information as a time series data to Elasticsearch so that we can view the data loss in the Kibana dashboard. Now, let's take a look at the data loss tracking dashboard. Here, the blue line on the top demonstrates the total number of messages produced to a specific Kafka topic. The orange chart shows the total number of messages consumed from the same topic by our specific consumer group. If the total number of consumed is equal to the total number of produced, we'll consider this no data loss. However, if the number of messages consumed is less than the number of messages produced, we'll consider these are data loss. So you can see here, these are a small gap, and we report data loss. However, I would like to mention, if we only use message count to detect the data loss, it's difficult to achieve 100% accuracy. Two reasons. One, in certain scenarios, duplicate message delivery may happen. Second, sometimes the message delivery may have delay. In these algorithms, we wait for a certain time for all the message get delivered to the consumer side to calculate the data loss. However, if certain message get really delayed, we'll consider it as a data loss, even though later on it may still arrive to the consumer side. Of course, we are going to continue improve these algorithms to improve the accuracy. And KPI dashboard and the data loss auditing build a strong foundation for our cluster and client visibility. However, the more and more use case onboarded, our cluster get overloaded, which impact the availability and the latency. This led to our next goal, onboarding and capacity management. Since we have Kafka users here, does anyone have already suffered to just onboard a new Kafka topic in a cluster? Nobody? Okay. In PayPal, it's different because we have so many customers, they want to use our cluster. We cannot just let customers to create a topic whenever they want. We have to control the topic creation to make sure we have enough capacity for them to use. So let's first take a look at the onboarding process we used before. So when users want to onboard our Kafka topic, they have to file our Jira ticket. In this ticket, they have to tell us the topic name, the message size, retention period, etc. Then after Kafka team receives the request, we'll do manual capacity assessment and create a topic if the capacity allows. And then after that, we notify customer the topic is created, and they can start to use this Kafka topic by produce message to it or consume message from it. However, because of the cross-team communication and the manual capacity assessment is very slow, it usually takes days to weeks for us to onboard a new use case. This was not acceptable. So when they improved this process by building our self-service onboarding, so in this new process, we provide our user a web-based user interface. So the customer can use this web UI to register the application and the topic requesting information. Upon submitting, our automated process will trigger the capacity assessment and the topic creation process if capacity is okay. And by this automated process, the onboarding is reduced from weeks to just a few minutes. So users are ready to start to use the Kafka topic to produce data. So let's take a look at our self-service onboarding UI here. You can see those those are all the data we take from the customer for them to register the application and the topic details. Okay. Next, let's look at the capacity management. PayPal has one of the largest Kafka deployment in the industry. Every year, we spend tens of millions of dollars in hardware to build Kafka clusters to serve our customers' need. So how to efficiently manage the capacity and reduce the cost became one of our major challenge. So in the past, we would allocate a capacity on a per cluster basis. What does this mean? This means we usually will assign our entire dedicated cluster to one big use case or our organization. But with time goes, some clusters become overloaded while some clusters are underutilized. That's because the customer's real usage is always different from their original requests. In addition, this model is also making it difficult to share data between different organizations. So to reduce the cost of the and utilize the Kafka cluster more efficiently, that we move to our cluster group model. In this cluster group model, we treat all the Kafka clusters in the same data center as one group. So any new use case can be onboarded to any cluster in the same group if capacity allows. With this new model, different organizations, they can share the same cluster capacity, and also it's easy for them to share data. More importantly, this allows us to migrate the load between different clusters if they are in the same group. So for example, if one cluster is overloaded, we can always move one topic from this overloaded cluster to another underutilized cluster in the same group, to still let the customer to send traffic to this topic without impact anything to the customer side. With this new cluster group model, there comes another challenge, because previously we can easily know how much capacity are used by each of the organization. However, with this group model, they share the same clusters, so it's difficult for us to know which organization used how much capacity. So to solve this problem, we further build our capacity showback. So this capacity showback will calculate and display the capacity usage for each organization and the customer. So it helps us to control the cost. Also, it builds the foundation for the pay-as-usage model. Currently, we don't charge our customers, but in the future, we may send different bills to different organizations based on the real hardware usage. Here is our initial version of the capacity showback UI. So you can see on this graph, it shows the disk usage of our organization within this time period. On this graph, it shows the disk and the network allocation among different organizations. So I don't know if you can see it clearly. Each color represents each different organization. So you can see here, Tushar's organization used most of our disk storage resource, and the AG's organization used most of the network bandwidth. So based on those data, and in the future, we'll send them different bills based on the hardware usage. Now I would like to hand over to MAULIN to talk about how do we do load migration between different clusters in the same cluster group by using our configuration service. Thanks.
All right. So why we built all these capabilities that we mentioned before? We had few concerns around the utilization of our clusters, as Na mentioned, and some of the availability challenges. Let's first look at the utilization. So as we mentioned that our clusters are multi-tenant. So as the different clients grew at different rates in our multi-tenant clusters, that resulted into uneven distribution or uneven utilization of our cluster over a period of time. Also, some of the clusters that we built very initially started to grow old in terms of machine configurations, and we needed to decommission them. Now, in order to utilize the clusters better or decommission the old clusters, essential ability we need is to move topics to different clusters and then move clients, right? Easy enough, right? Well, not so easy if you are dealing with polyglot client base like we do, and the polyglot client base we have, and the inherent difficulty in making sure that when we move topics, you have to retain the configurations of topics, which means the retention period, the replication factor, everything has to be the same as you move topics to different clusters. Now, not only that, you also have to make mirror maker changes correspondingly so that the mirroring is not broken when you move topics from one cluster to another. So, and the most challenging part of this whole movement is essentially the client movement, which we have to do. When we move the topics from one cluster to another, you have to make sure clients are also moved correspondingly. The challenging part there is that the clients, Kafka clients today, depend on the Kafka clusters in a tightly coupled way by using the bootstrap servers in their configuration. And that makes it very tightly coupled and very difficult to easily change them, because what it means is you have to change their code or config and then make the push to live. So, however, before we talk about how we solve these challenges, let's talk a little bit about some of the availability challenges that we had. For example, one of the challenges that we had was based on the Kafka broker and the client-side versions we were on at that time. Some of the producers started getting batch expiration errors. What are batch expiration errors? Anybody? So what it means is Kafka Java producer batches the messages before it delivers to the broker in order to utilize the network better. And when all the retries of the producer exhausts and beyond certain time a batch of a message cannot be delivered, it results into batch expiration errors. And then essentially what it means is producers cannot produce messages anymore. And this resulted into 0% send availability for those producers on those topics. Now, while we do the root cause analysis and all that, we could not block our clients from producing messages. So what we had to do was we had to take all the topics, impacted topics. In this picture, you see only one, but in this particular case, it was like a couple of topics, like 10s or 20s. We had to recreate those topics on different clusters, make all the mirror maker changes, and then give the client new bootstrap servers, which they had to do a code and config push to live in order to use it. The other challenge that we faced was sometimes due to network switch or power outages, our clusters become completely unavailable. And all of our clients on the cluster will obviously be complaining and filing high priority bugs for us to deal with. The challenge, other than the challenges we mentioned about how to move topics efficiently, here the challenge is we don't even know what topics were there on the cluster because we lose the connectivity to the cluster. So we can't even query the metadata. So how do you recreate the cluster? That becomes one of the biggest challenges for us. So again, we followed, somehow we managed, and we followed manual processes to fix the problems and bring up the clusters back. And what it meant for the clients, several days and hours of downtime which was completely unacceptable. So in order to overcome these challenges, we decided to do three things. First is to build the metadata about ecosystem, which means metadata about our clusters, topics on the clusters, and clients using those topics, and the relationships between all these three. The second, we decided to break the tight coupling between our clients and clusters via the Bootstrap servers. And third, we decided to build the automation around topic movement, which will help us take care of when you want to create topics, same topics on different clusters, making sure the configurations are retained and corresponding mirror maker changes are also done. Sorry, what's that? Bootstrap servers. So let's first talk about a configuration service which helped us in decoupling the clients from our clusters. And the way it works is the client application here, instead of using Bootstrap servers configuration in Kafka, they will call a configuration service with the set of topics they are interested in order to do produce or consume. The configuration service will in turn read the metadata that we built, which maintains all the data about topics, clusters, and clients, and what is their configuration, and return the set of Kafka properties, which typically Kafka clients use in order to initiate the Kafka client objects and talk to the clusters. And here, the Kafka properties will be depending upon whether the client app is a producer or a consumer, we would return the right set of properties, which will include the Bootstrap servers, where the topics are located currently. Then ultimately, Kafka client application will use these Kafka client properties to communicate to the cluster. Here, as you see in the diagram, we have PayPal client-side library, which our Java and Scala-based integrations through Kafka use in order to make the call to the configuration service. And the advantage of this is that we can push client-side configurations to the client applications. So instead of they configuring anything for Kafka, we can push configurations that we want them to use. The advantage here is that we can avoid the issues that are caused by client-side misconfigurations. For example, sometimes we used to get issues reported where it says our producers are losing messages. And what we found out was that the producers were using the ACK configuration as 0, essentially, and not doing asynchronous message sends. So they won't even know if the connectivity is the problem between the client and the cluster. They will not be able to send, and they will not even know. And they will think that the messages are lost. And we don't want our clients to have such misconfigurations, which leads to these problems. So apart from this, the other part of the equation is to have the movement of topics done easily. That we achieve through the admin service in our control plane, which essentially orchestrates this topic movement. So end to end, here is how it works. Let's say you want to move set of topics from one cluster to another. We, as an admin, will come to the admin service in the control plane, will trigger the commands to initiate the topic movement. What will that do is it will set up, it will pick the configurations, it will read the metadata, it will pick the right topic configurations for the topic, it will replicate those topics on different cluster, it will make all the required mirror maker changes, and then get the setup ready. And then, once that is done, we coordinate with client applications. Since we know the metadata about all the applications using the clusters and topics, we coordinate with client applications to perform restarts. And when they restart, they pick up, they again end up calling the configuration service, which gives them a new location of the topics, and they start producing and consuming from that. So Now, with all of these features and capabilities, we moved away from earlier manual, error-prone, and unpredictable processes, which resulted into several hours of downtime for our clients, to automated, streamlined, and predictable process, which helps us reduce the downtime to a few minutes, which is a great improvement for us. So next, let's talk a little bit about the Kafka control and data plane that we have. And we'll start from this component here, presentation layer in our control plane. So the presentation layer in the control plane has two sets of users, as you see in the diagram, admin and other clients. The admin users come to this presentation layer in order to perform admin tasks on our Kafka brokers. For example, like creating a topic or initiating a topic movement, right? The other clients come to the presentation layer in order to perform tasks such as onboard their new use cases to the Kafka ecosystem and looking at their KPIs like latency and fetch availability and stuff. And the role-based access control in the presentation layer separates two sets of users from each other. Next, we'll talk about few of the components in the control plane. And we'll start with admin service. So we have pretty complex network and deployment topology at PayPal, which we have to navigate through in order to operate our clusters. Because clusters are deployed in different networking regions and security regions, and we have to make sure that we are able to operate on them. So the admin service helps us navigate through that complexity in much easier way by having one central place like presentation layer and to be able to operate all these clusters. The mirror maker management component helps us in building all these abilities that we need in order to automate the mirroring related challenges. Like when we move the topics, we have to make mirror maker changes, right? Of course, it helps in setting up new mirror makers or tearing down all mirror makers. It also addresses concerns around the capacity management, like how do you know how many mirror maker hosts you need to run the process on, for example. The configuration service, as we mentioned before, essentially helps us in decoupling our clients from our clusters and provides ability for us to manage the clusters without tightly coupled clients attached to it. The last but not the least is the data plane components in our data plane, like Zookeeper, brokers, mirror makers, and the metadata, can only be accessed through the components here in the control plane. And why is this important for us? Is because how we mentioned the component called KafkaMon before, right? That when we initiated in end of 2015, it was hosted on like a couple of boxes just to have HA for the monitoring itself. However, those couple of boxes have to have access to all of our clusters, which spans across our networking and security zones. And that was violating a lot of policies, networking and security policies. And this new design of control plane and the data plane helps us comply to those policies. So with all of this, heading to the future, what we are looking to focus more on is automate the client failovers. How we mentioned that we have to, after making all the configuration changes and setup changes from the admin service, we have to coordinate the restarts of client applications. So next step obviously is to automate that and not require clients to even restart and automatically pick up based on some timing. The second area that we want to focus on is we want to automate some of the remediation processes that we run today. Like topic repartitioning and other things that we do as part of Kafka management. And of course, continuing the contribution to the community. For example, the bug fix here that recently got merged to Kafka in Apache. And making more open source contributions like client-side KPIs that we talked about, send and fetch availability. And of course, sharing our learnings and experiences through forums like this, where we can share what we experience and how we resolve those problems and how do you scale with those challenges. So what's the conclusion? So today we talked about the challenges that we faced in scaling Kafka at PayPal. And we hope that you feel that how managing Kafka without proper tooling can really become unmanageable in the long run. We also hope that you realize the work ahead of you in order to scale Kafka for your use case, dependent upon size and structure of your organization. And lastly, we certainly hope that all these ideas and approaches that we presented here provide good templates for your thoughts, and you do take them up to the extent applicable to your use cases and make it work for you. And with that, we would like to thank for your time. And now, thank you for saving all your questions. We can take the questions.
Change our course with the wind. Found my better me in the small things you see, discovering a home again. When the day fades away and there's nothing left to say, I'll read your thoughts.